Ladies and gentlemen, welcome to our last lecture for this semester, and then we will take a break because college will close its doors, and then immediately in September I will come up probably with 200 pages written for you. No, I'm joking, but this how now goes with AI. I'm just asking and extracting from AI. Everything is written in code, all the programs. I mean, amazing. For me, it's just phenomenal. So we have learned a lot, mainly about mathematics, but then we are planning, we will develop this machinery, and then we will be able to take physics on a little higher level in programming. But yes, one professor said that mathematics, maybe someone before him said that it's a language of nature, and I would really agree. And some they argue also that we are just discovering math that was actually that is already there. We just need to discover how those things work or relate and how that functions. So I would say that in some sense it's the language of God because God created nature and He created mathematics as well. So we are doing divine things. And let's get started. Today's lecture, I was doing economics. I was planning to do just a few pages for the last lecture, but then I just couldn't stop because I said I need to explain this and that and this, and you will see we will go quickly through. And then follows probability that we finish with Stirling numbers, and then we have surprise code for you, and finally, as many times, some surprise animals. So let's get started. So welcome to Economics 3. Today no biography, just very important topic of supply and demand. This is a topic of microeconomics because we look at just one commodity, although there are many more people involved. So macroeconomics would be GDP as a whole country and things like that, unemployment and so on. And we are examining the case of illicit drugs, particularly cocaine. We want to know what is happening with cocaine. And we first look at demand. And here we have price, and here we have quantity. And what happens? When cocaine is very expensive, the demand for it is very low because people don't have so much money. I think it's very expensive, as you know, I don't know how much, $100 a gram. So they won't buy it. But if it would be very cheap, €5, €10, then the quantity would skyrocket, everyone would want it, and society would probably change. So that's how demand works. And yes, what is this curve? Here it's written that y is actually x, some constant, divided by x, and as we will see in the continuation, this is actually inverted for 45 degrees rotated hyperbola, but it can be also linear, it can be any function, it can be parabola to the power of alpha, as we will see later, which actually more describes use of cocaine because it goes something like this, and here is very steep, so inelastic, but here becomes very much elastic. And what this means here that users that use cocaine are usually quite rich, and if you have 100 millions, you don't care if the price goes up. You will buy it anyway because you need it. And how is it supplied? It's actually similar price and quantity, and when the price is low, if it would be just $5 a gram, nobody would want to supply it and nobody would want to work for it because they would barely make a living with it. But if the price will go up, of course everyone will want to produce it, everyone will want to earn the money. Not everyone, because who don't want to risk to be caught wouldn't do it. And here again, we have here parabola, y is some constant b times x squared. And we could use exponent function e to the power of x, and we could use also linear function bx plus c, as we will see in right now. think I had lost some weight. I was watching and said, good. So, how is this hyperbola? Rotated hyperbola in new coordinates, capital X and Y, and with vector X. And now you will see the tensor algebra also in economics and calculus as well. Is our rotational metric, we said Q, some use R, that matter times vector X, the old coordinates, and this in vector form, in expanded form, vector X, Y. And here is 1 divided by square root of 2 because cosine and sine 45 degrees is 1 divided by square root of 2 or minus. And this matrix times vector, you get this vector, and inserting this into the equation of hyperbola, where here you say 2k, and you get that y is k divided by x, or we said a divided by x in our case. And now elasticity, another important subject of economics, is actually divided as change in quantity divided by change in price. And that is delta x divided by x divided by delta y divided by y. And rearranging this, we get this, and we know that if we take the limit where delta y goes to 0, this is derivative. And so dx dy times y divided by x, or 1 divided by y prime times yx is elasticity. And if you calculate it for hyperbola, you get constant elasticity of minus 1. So yes, if you want more steep demand curve at the beginning and later more flat, we can use generalized hyperbola, which is a times h to the power minus alpha. And elasticity is no more constant in that case, but it is 1 divided by alpha. In our nonlinear model, let's say we have just parabola, hyperbola and parabola as a supply, and these are the blue curves, and E0 is equilibrium. In this equilibrium, here it will stop, because people are willing to pay so much and so much is supplied, and they come into equilibrium. I mean, you can imagine somewhere stops. And then what happens? It goes to shift. Maybe police sees much of the supply, and supply moves to the left, horizontally shift to the left, and demand, maybe it's, the good voice goes around and they say it's really good, and demand goes to the right. And we see the price goes up, but we don't know quantity, whether it goes more or less, as we will see further. But how do we do this shift? We just simply x minus d right here instead of x, and equate this with supply. And instead of x squared is now x minus s squared. And we expand this equation, and we see that we get a cubic equation in x to the power of 3, 2, x, and constant. And we will learn later in tensor algebra how to solve this. This Cardano solution is analytical, but it's quite complicated, but we can solve numerically actually any polynomial. How actually to choose this curve, demand or supply, whether it's linear or non-linear. You need to know the case, and in fact we don't know exactly, so we're just approximating what we think is best. And usually, if you look at this one, hyperbola and linear graph is actually important. Some use this because if double quantity means double price in both cases. So you will have there a Python program, and you can move x and d and shift them left or right, and you will see how they move. Everything is done for you for non-linear case. And linear model is similar. You will have linear and non-linear model, both cases. And linear, you define those two lines and equate them as before, and you get the x and y of this shift to the new position. So yes, what is here? Demand, supply. If you shift them horizontally right or left, and here price goes up, price goes down, and then we don't know, it can go either up or down. And similarly for quantity, we don't know, and here goes up, and here goes down. And finally, instead of shifting, we could actually scale the equation. And in non-linear cases, we would change A and B, in linear MD and MT. And this actually represents if more users or more suppliers come to the game, and then we're just summing up those curves. And here be careful, these curves can look as this if you change the scales on the graph. And similarly for B, for parabola, we are just summing them and we are moving here. And again, if you would stretch this, the curves could look the same. And in either case, again, we are summing the curves, and here also. So this is alternative to this, or you can say when you sum the participants. So that will be it from economics, and now let's go to probability and statistics. So welcome to lecture 8. I didn't change my clothes. It will be a little different, so we will know that we switched more, it's more emphasized. So just from before, monomial x to the power of n, we said is one sum, and then we inserted Stirling factorial, and we actually got two sums, and then we rearranged them. We got those products, which you know that is delta chronicle delta tensor, delta n, and this one we said that switches the index. You see here it switches n to n, and some drops out, so it's the same x to the power of n. To clarify. Now we go to Stirling numbers of the second kind, and we do all four cases as we did for the first kind. And first one was labeled fish, labeled aquariums. If you have n is 5 fish and 3 aquariums, and they can be empty or not, how many fish, how many ways is to do that is k to the power of n 243 ways. But this can be also evaluated as a sum of binomial k over n times k minus n factorial times Stirling numbers of the second kind n over k minus n. And you sum n. Here you should, instead of n, you should choose j, and here go from 0 to n. But you will get, and everything is also written for you. So if we continue that example, n is 5 fish, k is 3 aquariums that can be empty, unlabeled, labeled, we get the same as in Stirling numbers of the first time. Actually here no Stirling numbers at all. And labeled, unlabeled is just a sum of Stirling numbers from r is 1 to 3. And unlabeled is again Euler partition formula, or by intuition, whichever you prefer. Recurrence relation can be again derived intuitively, whether the additional one fish joins separate group, or if it joins in one of those groups, times k, you get recurrence relation, similar as for Stirling numbers of the first kind. And two important relations are derived in the report for you, and that is the multinomial formula is actually the same as r factorial times n over r Stirling second kind, and similar for the first kind, where you use c, which are lengths of individual cycles, to get those two relations. Then you have the tables that you show you explicitly how we do the for Stirlings of first kind and second kind, and if you sum them, you will get a program, and program you can do by yourself. It's actually very similar as we have as the first one, just that you put instead of Stirling numbers of the first kind, you put Stirling numbers of the second kind. And for the final challenge at the end of semester, we prepared you a code you will be playing, and it's a little computer art, I would say, in mathematics. It's called as game of life. And what is it all about? You have pixels, a grid of pixels, and they can be either 1 shown or 0. And in our program we will also have how much they last, they can also change colors. And you will be able to play with this. You will say AI or do by yourself as you wish to incorporate new regimes and new rules. And what it's all about, we look at the pixel, and pixel is either live or dead, and we are looking all surrounding pixels. And if less than 2 surrounding pixels, if pixel is live, lives, and is less than 2 surrounding pixels live, then becomes dead. If lives and 2 or 3 are live, then lives. And if more than 3 when lives, then dies. And if it's dead, if there are exactly 3 life, then leaves again. And in our program, Conscious Game of Life, I said, let's do more and let's look also at members of the members. So it's bigger metrics, and I said, just make up the rules, and you can ask, just paste the code, you'll get everything on the internet page as always, and say what is the rule, and you will get it. Then now the animation will play, and I also made music with AI, so it will play for you around 3 minutes. And that would be it for the end of our first semester. I didn't know how this will go, but with the tools that I received, I think it's really amazing. I myself am surprised how this AI functions and how it understands what I want. So I'm really thankful to everyone who was watching, and I hope you like it, even if you didn't understand it, you just understood approximately what we were doing. And I hope we see us in next semester. I mean, I will maybe do some videos, but not lectures, and that you will be with us, and that we will have some more interesting things. Now we know how this goes. And again, thank you, ladies and gentlemen, for your attention. Have a nice holidays, and see you soon. Enjoy. They know here I'm sitting, and they go up, and then they throw something down on the table so that I know, and that I give them the food. And now they're waiting. You will see this. And there are more. Here is one, another one, and I'll give them to each one. I'm trying, because they fight sometimes.
And you. Let's see, and that one get. They're really smart animals.